Today, we're going to create this cool animated cloud pattern. Let's go. So, we're in the middle of a series of tutorial videos about creating procedural shapes and patterns. The main value in this series is the library of material functions that we've been creating so far. You can see here as I scroll through these folders, all of these material functions are what we've created in the series. These can be combined together to create all kinds of effects. If you haven't seen the previous videos in the series, I'll link the playlist in the description down below so you can catch up. Today, we're going to create a new material function for creating this animated cloud pattern in Unreal. And then in a minute, we'll jump over to Unity and I'll show you how to make a similar material function there. All right, let's get started. So the first thing that we're going to do is come down here to our content drawer and we're going to come here to the patterns folder, shaders, procedural patterns. And I'm going to right click and pick material function. And we're going to call this animated clouds. And I'll double click it and open it up so we can get started. All right, let me show you the core of this effect. I'm just going to open up my menu here and type noise, and we're going to bring in a noise node. And just so you can see what's going on, let's plug this into our output result. And you can see here that I'm getting some nice looking noise. I'm going to change this to unlit for now, just so we don't get distracted by any lighting. All right, this noise node has a lot of settings. So let's come down here and take a look at the settings. Obviously, right now our scale is kind of off. So let's change this to 0.05. And you can see now that it's generating this noisy pattern. We can make it even smaller and take a look. Yeah, so we're getting some noise. That looks pretty good. You can see I've got the controls for output minimum and output maximum. And if I set my output minimum to 0, now you can see that we've got something just a little bit more reasonable. And right now, like by default, the noise has turbulence on. But in the kind of noise that we're creating, I don't want turbulence. So I'll just turn that off. All right, so we've got this noise node and it's generating a really interesting pattern for us. Now, the most important setting over here is this drop down called function. And if we take a look here, you can see there's a bunch of available options. And this is very important for the performance of the effect. We're going to pick fast gradient 3D texture for our noise, because that's going to give us the best performance. It's the cheapest version of this effect. And the other thing that we're going to do is we're going to change levels. Noise is generated by running an algorithm over and over. And each of the times that this run, it's called a level or an octave. And every time I run it, it gets more expensive. It's basically doing the same thing again and again and again. And in our case, we can get away with only doing 3 octaves. And so I'm going to turn my levels down to 3. That's going to make my noise significantly cheaper. All right, I think those are all of the settings that we need to set on the noise for now. The other thing that I want to do, most of the effects that we've been creating in the series so far have been using UV coordinates. And this time, what we're going to do is project this pattern in screen space so that the pattern will stay relative to the screen instead of relative to the surface of whatever we're applying it to. So let's go ahead and set up our UV coordinates that we're going to pass in. And we're going to do something really interesting with the UV coordinates. So be sure that you pay close attention to what we're going to do here. So the first thing that we're going to do is bring in the screen position node. And if I pick the viewport UV output here, Let's just go ahead and temporarily plug this into our output so that we can see what this is doing. All right, so what you're going to see here is up here in the upper left corner, we get a value of 0. And our UV coordinates go from 0 to 1 on the horizontal axis. So over here, we've got a 1 in the red channel. And they go from 0 to 1 in the vertical axis as well. So down here, we've got a 1 in the green channel. So what I'm seeing here is the coordinates of the screen. Now, in our case, we're applying this to, or we have a square viewport. Let me see if I can make this viewport non-square. If I just change the aspect ratio here, now you can see I've got 0 to 1 on this short axis, on the vertical axis, but 0 to 1 on this long axis here. And our viewport is not square, which means that our noise pattern is not going to be square either. And we want to correct this so that regardless of the aspect ratio of the screen we're applying it to, our coordinates are always going to be square so that they maintain the proper aspect ratio of the noise. Even if we have a screen that's long and thin, we don't want our noise pattern when it gets projected to look like it's stretched. And so the way that we're going to do this, the way that we're going to make our screen position coordinates square, is we're going to bring in the screen resolution node. And this is going to give us, if we take the output of the visible resolution, it's going to give us the value or the number of pixels across and the number of pixels down. And so what I'm going to do here is I'm going to create a component mask, and we're going to calculate the aspect ratio of the screen by dividing the width by the height. So I'm just going to split out the red and the green. And then we're going to divide these. We'll divide the red channel by the green channel. And what this is going to give us is the ratio of the width to the height. And so now I can take this value and append it together with a value of 1. So this is going to be my first value, and then I'll just take a hard-coded value of 1 and plug this into my second value. And now I can multiply this value by my screen position here to get coordinates that are square. So if we take our screen position and multiply it, now let's pass the result of this in. And what we're going to see is no matter the aspect ratio of the screen, we're always going to be getting a square result. Just to make it a little bit more obvious what's happening here, I'm going to add a frac node and we'll drag it in. And what you'll see is that when the screen is long and thin like this, our UV coordinates are repeating over and over. And as I make the aspect ratio more square, it's no longer repeating. And so our UV coordinates are maintaining a square aspect ratio regardless of the aspect ratio of the size of the screen. And that's the result we want, because we want our noise pattern to maintain its aspect ratio. We want it to be projected in screen space, but we want it to maintain its aspect ratio regardless of the aspect ratio of the screen. Hope that makes sense. Okay, the next thing that we need to do is we want our noise to be animated. And so in order to create animation, we're going to bring in time, and we're going to multiply time by a parameter that we can use to control the speed. So I'm going to bring in a function input, and we're going to set our function input to be a scalar value, and we'll call it time. And we're going to multiply, let's see, for the default of time, I want this to move kind of slow, and so I'm going to set this to 0.05 as default. And I'll come down here and set use preview value as default. And then we'll plug this into our multiply node here. So we're multiplying time by our speed parameter. All right, I want to explain something important about this noise here. And that is, can you see how it says fast gradient 3D texture? This noise is actually being generated in 3D space. And by default, can you see this world position input? By default, it's using the world space position in X, Y, and Z to create the noise. Now I know that it looks two-dimensional here because it's being applied to a two-dimensional surface. But if I had a volume here, you'd see that this noise is actually three-dimensional. Let me see if I can change this to a cube. And if we take a look here, you can see that here is on the front face of the cube here, you can see one facet of the noise. But then as we scroll around to the side, you can also see that the noise is three-dimensional, so it's projected through 3D space. And you can see that it wraps around the sides. In other words, so there's no seam here. It's not being applied in 2D, it's being applied in 3D. And so if I want to create a 2D animated effect, I can use my UV coordinates for the width and the height parameter, but then for the depth parameter, I can use time. And this is the really interesting part about the coordinates for the noise that we're going to use today. So instead of using depth for this third dimension, I'm going to use time. And what that's going to do is it's going to animate the noise and push it through the two-dimensional space with time as the third dimension. So let's change this back to our plane, and we'll move it in here. All right, and then what I need to do is add an append node, and we're going to take the screen position coordinates and plug that into our append. And then we're going to take our time multiplied by our speed and plug that in as the third component of our coordinates here. So we've got screen space, horizontal and vertical as our first two coordinates. And then our third coordinate is the value of time. So now in my noise here, instead of world position, I can plug in this value. And now we're going to get some animated noise. You don't see it very well here because I need to change the scale value. So let's grab our noise here. We've got our scale set to 0.01, and that worked really well when we had our coordinates set to world position. But right now, because we're using screen position and time as our coordinates, I need to change our scale to something like 5. Yeah, perfect. All right, so what's happening here is I've got my screen position, horizontal and vertical coordinates, and then I'm using time as that third coordinate, and it's moving the volume of the noise toward the camera. And as the volume moves, the noise animates. Pretty cool. Okay, there are just a few little finishing touches that I need to add. First of all, I've got my noise, I need to adjust the gamma of the noise. And so in order to do that, I'm going to add a power node, and we're going to raise the value of the noise by a power of 2.2. And this is going to make the noise balanced a little bit more toward the black levels. Before, it was kind of pushing toward bright, and I've just adjusted the gamma curve so that we get a little bit more balance between black and white here. Okay, now to give the user a little bit more control over the output here, we're going to use a lerp node and blend between a couple of custom colors. So I'm going to create a function input here that's a vector 3, and we'll default this to 1, 1, and 1. So we'll make the first color white, and I'm going to call it color 1. And we'll bring in another one and call this color 2. And just by default, we're going to make this one black. So we'll plug in color 1 to lerp A and plug in color 2 to lerp B. And now we'll plug in this to the output. And now you can see that we've given the user control over what colors to use. We've got white and black. And actually, let's swap these. Let's make the default black as the first value and white as the second value. And because we've done it that way, you're not going to see any difference between what we're doing here and what we already had before it. So just looking at the preview of this, actually if I set enable preview for this, or if I set enable preview for this, they're going to look exactly the same. But what this is going to do is allow the user to customize these colors using these inputs, so they can put in whatever colors they want. All right, that is how we create our animated noise pattern. And what's interesting here is because we're projecting this in screen space, no matter how I rotate this around or how much I zoom in and out, the pattern is going to stay the same. It's being projected in screen space rather than projected in UV space. Okay, so just a couple of finishing touches here. I'm going to come over to our inputs. Oh, interesting. You know what? I never created an input for our UV coordinates, but we do want the user to be able to create their own UVs in case they don't want screen position. And so for inputs, I'm going to call this one UV, and we'll set this to a vector 2. And the coordinates that we created for the screen position, these are going to be the default input. So I'm going to drag this over and plug it into the default input pin here for our input UV. Then we'll plug this into our append, and that's going to allow the user to input their own UVs if they want. And as always, I need to make sure that we check use preview value as default. Okay, so this is going to be my first input, and so I come down here and set sort priority to 0. Let's see, I want my colors to be my second input, so I'm going to set the sort priority on this one to 1, and the sort priority on color 2 to 2, and then my last input here is time, so we'll set the sort priority on that one to 3. Okay, and then the last thing that we can do is just kind of, for convenience, we can set a description here. I can say something like creates an animated cloud pattern. And now we want to add this to our library. And so I'm going to check this expose to library box. And down here where it says library categories text, let's see, if we look here in our library, we'll come down here to procedural. We want this to go into the procedural / patterns category. And so I'm going to call this procedural patterns. And when we save it, now let's take a look. I don't know if it'll show up in itself, but it does, yeah. So we've got it here listed under procedural patterns, animated clouds. Okay, cool. So that's our tutorial for today, creating this cool animated cloud pattern. Next week, we're going to use this animated cloud pattern to create a cool sci-fi effect. But before we do that, today we're going to switch over to Unity, and I'm going to show you how to make this same thing there. All right, here we are in Unity. And just like we did in Unreal, we're going to create the animated cloud pattern. So in order to get started, I'm going to come over here to our patterns folder and right click and pick create shader graph subgraph. And we're going to call this animated clouds. All right, so I'll open up our animated clouds subgraph, and we're ready to get started. Now there's one main difference between the way that we created things in Unreal and the way that we're going to make them in Unity. In Unreal, we had a node that allowed us to create 3-dimensional noise, but Unity's noise is in 2D, and so if we want to create these animated clouds, we need to use the 2D noise instead. And so I'm going to use the simple noise node. And in order to create this animation, we're going to scroll this simple noise node across itself, and we're going to use 3 different copies of it. So for this first copy, I'm going to set the scale to 13. For each of the copies, we're going to set the scale differently so that we don't see a repeating pattern lining up with itself. So I'm going to set it to 13, 15, and 14 just to give these a little bit of variation. And that way, when they're scrolling, they don't ever like overlap each other perfectly. All right, so we've got our simple noise here. And what we can do is take this noise and add it all up. So I'm just going to add the first one with the second one, and then add the results of that with the third one. And now we've got noise that's like 3 times as bright as it needs to be. And so in order to fix that problem, we can just add a multiply and multiply by 0.33, and that'll bring it back down to something a little bit more realistic. All right, but before we get too far with our noise here, I want to show you what we're going to do with our UV coordinates. So let's come over here, and the first thing that we're going to do is come over here to our blackboard and add a new vector2 parameter, and we'll call this UV. And I'll select our parameter, and then over here in the graph settings, we're going to pick Use Custom Binding. And usually we type UV0 here, but in this case, we're going to type Screen Position, and that's going to be our default for projecting. And I'm going to show you in just a minute how to set this up. But first, we're going to create a branch on input connection node. And I'm going to connect my UV input parameter to the input and the connected. And now for this not connected input, we're going to set up the default. And we're going to create screen position coordinates. So I'm going to bring in the screen position node. And what this is going to do is it's going to give me a value that determines where in screen position we are. So if we open this up, in Unreal, 0, 0 is up here in the top left, but in Unity, it's in the bottom left. So we're going to take our screen position, and by default, it's a float 4 or a vector 4, but we only want the first 2 components, the X and the Y. And so I'm going to add a swizzle and just type XY so that we can filter out the Z and the W components and just have a vector 2. You can see this output is green here and it says 2. So we have a vector 2 coming out of there. And these will be our coordinates for projection. But just like we did in Unreal, we want our coordinates to be square. And if our screen size is stretched, we'll end up with stretched noise if we just use these UV coordinates as they are. So in order to fix that, we need to bring in the screen node. And here you can see we've got the width and the height of our screen. And we can calculate the aspect ratio by just dividing the width by the height. So now what we can do, I'm going to add a combine node here because we just want to multiply this by the X component of our screen position. So we're going to plug this into X. And then in the combine, we're going to type 1 here for the default for the second component of our combine. And then coming out of the combine, we're just going to use this R and G value because we just need a vector 2. And we can multiply our screen coordinates by this aspect ratio that we've calculated here. So what this is doing is giving us coordinates that are now square, and no matter how stretched or tall the screen ends up, we'll always get square coordinates and therefore square noise projection. Okay, so these are the default coordinates that we've created. And this is what will be used if the user doesn't put anything into this input that's called UV. All right, so we've got our UV coordinates and we've got our noise over here. But if we plug our UV coordinates in as is, the next thing that we need to do is bring in time so that we can have animation because we want to scroll our noise. So here's our time node. and we want to multiply time by speed. So I'm going to add another float parameter here and call it speed. And we're going to default speed to value of 0.05 because we want our time to move kind of slowly. All right, then I'll bring in our speed parameter and we're going to multiply it by time. Okay, so this is the value that we can use to control how fast the noise is scrolling. Okay, the next thing that we need to do is set up 3 different variations of our UV coordinates. We've got our UVs here, and we've got our speed. The first one that we're going to create, the first variation, is just subtracting time from speed. And we're going to plug this set of coordinates in here. And now you can see that our coordinates are scrolling up and to the right. But we can't use this same set of coordinates for all 3 of our noise patterns because then our noise, we want our noise to animate, but we want it to look like it's staying in place. And so we need to create 2 other variations. The next variation that we're going to create is going to be adding it, so it'll scroll in the opposite direction. But we're going to take our UV coordinates here. Oh, you know what? There's a parameter that I forgot to add. And that is a vector2 or scale. And in fact, I forgot to add this completely in the Unreal version. So if you were working on Unreal, you might want to go back and add in this scale parameter. It's pretty simple. I'm going to default it to 1. And we're just going to add it as a multiplier for our coordinates here. So the coordinates are coming out of our branch on input connection. And we're just going to multiply it by our scale parameter like that. Okay, so we're going to take our UV coordinates coming out of here, and we're going to add a flip node. And what the flip node allows us to do is for any of our input channels, we can flip them or invert them individually. So I'm going to invert the red channel, but not the green channel. And then we're going to take the resulting coordinates and add them together with time. And now if we plug these coordinates into our second noise node, you can see that now what we've done is this one is scrolling up and to the right, and this one is scrolling down and to the right. And that's going to give us an interesting pattern and variation when we combine them together. In fact, we can kind of see what's going on over here, but you can still see there's sort of this overall direction that's going to the right, and we want to eliminate that overall direction. And so we need to create a third set of UV coordinates for our third noise here that changes the noise so that it moves in the opposite direction. And the way that we can do that is if we take our time here and add a negate. Now this is going to be moving in the opposite direction, but we only want to add this to the x parameter or the x coordinate. And so we're going to add a combine node, and for the y component, we're just going to set time to be 0. So now I can take our flipped UV coordinates here and add them together with the negated time that we've created. And now when we pass this set of coordinates into our third noise node here, now you can see that our noise is moving in the opposite direction. So we've got scrolling up and to the left, down and to the left, and to the right. And the effect of combining these 3 together is that we get noise that doesn't have a direction really. It's just kind of undulating and staying in place. And that's pretty cool. But what you'll notice now is that our noise is mostly, or that our noise is too bright. There's not enough contrast here, and we're not getting a good balance between black and white. And so we need to adjust the range of the noise. And the way that I'm going to do that is with an inverse lerp node. So I'll just plug our noise into the T input of an inverse lerp. And now to adjust the contrast, I'm going to set the A input to 0.18, and I'm going to set the B input to 0.8. And that's going to just give us a little bit more black. And then we'll add a saturate node, and then I'm going to raise our noise to a power of 2.2 to adjust the gamma. And we should end up with noise that has a little bit better balance between black and white. Yeah, that's what you can see here. And you can see we're getting this nice kind of undulating animated pattern that doesn't have any specific direction. And we were able to do that because we combined the 3 different scrolling directions together. So now our noise just looks like it's moving and animating with itself, but not actually moving in any one specific direction. All right, let's clean up our graph a little bit. We're just about done, but we still need to give the user control over the colors that are being blended together. So in order to do that, we're going to add 2 new components here in our blackboard. We're going to add a color 1, and we're going to add a color 2. And then we're going to blend between these 2 color values. Actually, let's set some defaults. We'll set color 1 to be black and color 2 to be white. And then we'll bring in these parameters. We're going to add a lerp node that allows us to blend these 2 values. And then obviously the T value of our lerp is going to be the noise mask that we've created so far. All right, so we've got color 1 and color 2. And by default, these are black and white, but we could set them to anything we want. You know, we could set these to like a orange value for color 1 and maybe a purple value for color 2. All right, so there we are with orange and purple. We've got this kind of orangey color and this purpley color. Yeah, so you can set these colors to whatever you want and create a pattern that suits your needs for you know, whatever thing you're creating. But that's why we've given the user the ability to customize these so they can make their pattern blend between whatever 2 colors works for them. All right, so we're going to output the result here. And instead of out vector 4, I'm just going to call this out. Yeah, and so we're all done. There's just a couple of last things that we want to do here. Come over here to where it says subgraphs. And we'll set this to procedural/patterns. And we set that so that when we add it, so that when we open our create node menu, it'll show up here under procedural patterns. And also the last thing that we need to do is come over to our graph settings and set our preview value to preview 2D so that it'll have a nice 2D preview on it. Okay, so we've got an animated clouds node now. If we come down here to our patterns, we've got our animated clouds. And next week, we're going to be adding our animated clouds to a new effect. This is going to be a background pattern that we create that's kind of a sci-fi background. And that's going to be really cool looking. So I hope you come back next week to see how we use our animated clouds to create that neat animated background. All right, thanks for watching, everybody, and have a great week.